So, right. So this is a very important topic. I'm going to start with a few examples, then we're going to look at how do you estimate the runtime for a program. And then we're going to talk about the complexity theory. How do you find the complexity for programs? So this particular course, we're just going to have a very basic idea about complexity. There's three ways or three asymptotic notations that we use. We're going to study only one of them, which is called the worst case analysis. Now, this particular course is divided into two courses. This course is about data structures and analysis of algorithms. So we learn about the basic data structures, and we see we learn the basics of complexity theory, and we see how we can compare the different programs. After you finish this course, for the computer science students, they will go and take the algorithms course. The algorithms course is continuation of this one. In that course, you're going to talk about the different paradigms for algorithm. You're going to learn about the bounds and more advanced topics in complexity. So here in this course, we're going to look at basics. Of course, when we're studying the complexity theory, there's going to be some mathematics involved. Generally, teaching students here in this university, most of the people are scared of lots of maths. But there are certain things that need to be covered, so basics and fundamentals. So we'll go there. Whenever you feel like you're not understanding something, you can ask away. I will be happy to repeat it. Okay? So having said that, let's start talking about analysis of algorithms. Okay, so quickly, you can see the picture in front of you. There's an orange. Okay, algorithm is like a machinery. So we use an algorithm to take the juice out of the orange. So an algorithm takes an input, and of course it provides some kind of output. The idea is that you're going to have some kind of problem. We would like to solve that using some algorithm, and we're going to have a solution afterwards. Now, the idea is there can be many number of solutions. For instance, if I give you a problem and I ask all of you to come up with a solution, there's very little chance that two people will come up with the exact same solution. Everybody has his own way of describing the problem, addressing the problem, okay, coming up with a solution and providing the solution. So now the question is, how do we determine whose solution is the best solution? So that's quite hard. And here we're going to address this issue. We're going to look at a specific notation that we use to take care of these things. Okay, so these are slides which are posted on my website. You can go have a look at them. Here's a little bit of history about algorithms. You see a photo in front of you that looks like an ancient machinery. This is in fact the analytical engine, one of the first calculators. Now you can see, if you look closely, you can see that there is chains, there's gears, there's a lever. The purpose for the lever is that you rotate it to move the gears, and the gears would move the chains, okay? And you can do simple calculations with this machine.
So this is more like a calculator than a computer?
Sorry?
Is it more like a calculator than a computer? Because is it like an actual computer, or is it just like simple calculation?
No, this was invented in 1864, around 150 years ago, by a gentleman called Charles Babbage. Okay, so in those days there was no electricity. I'm sure you're familiar with bicycles. Maybe when you were kids, or maybe sometimes people do ride bicycles here and there. Bicycles have gears, levers, and chains. So this machine is using similar kind of mechanism to do computation. So you can add a few numbers, okay? All you have to do is you have to rotate the lever. You have to crank it a number of times to do the calculations. So for instance, if I would like to add 8 plus 7, okay, I'm going to rotate the lever 8 times and then again 7 times, okay, to get the appropriate answer. Again, you can see this thing, there's no screens there. Of course, there was no electricity at the time. Now, the problem is, for larger values, you would have to move the lever many number of times, which can be time-consuming, it requires energy, and I don't know, eventually you're going to become a bodybuilder after you keep using this machine. Nowadays, we have modern ways of doing things, okay? We can time programs, how long a program takes to run. We can use a simple stopwatch, okay? Or we can build it into our code. I'm sure in CS101, you've studied some code, okay, that allows you to check the time of the system. So if I want to find out how long would my program take, what I can do is I can call this time system call, okay, before and after the program finishes. And then you can subtract the value to see how long did the program take. It's coming on the next slide. Now, here's something that I want to show you. There's a program which is called 3sum, okay? It adds values in very simple terms. Now, what we do is we create some text files containing some numbers, and we expect the program to run and add up the 3 values, the 3 sums. And what we do is we time it. We see how long did it take to complete the execution. You can see this thing on the right side. First, we run this program with a file that contains 1,000 integers, okay? And after I run it on this computer, let's say it took 17 milliseconds. Then I repeat the same thing. I repeat the same thing. I call the same program with a different file. This file contains 2,000 integers. It took 528 milliseconds. Again, I repeat the same experiment with a large data set. This time I'm using 4,000 integers, and it took 4,039 seconds. Do you see a pattern here? Or do you see that this something is wrong there? So for 1,000 integers, it took 70 milliseconds. 2,000 was 528, and 4,000, it took 4,000 milliseconds. Do you think this is fine?
It's gradually increasing.
Yeah, of course it's increasing, but I don't see a pattern. Yani 1,000 means it should take 1,000 seconds. 2,000 should take 2,000 seconds. 4,000 should take 4,000 seconds. But here you can see that the time is exceeding. Okay, for 1,000 it's only 70, and for 4,000 it's 4,000 milliseconds. So this means that we have to understand that when you run the programs, when the programs crunch the data, they work with the data, the size of the data also matters. We'll talk about this thing later. Okay. So here's the code that I was talking about. We can write code to build your own stopwatch. Okay, all you have to do is call this system call. You can say system.currentTime in milliseconds. Have we studied this in CS101? Anybody? Are you guys still there?
Yes, but
I don't remember, Doctor, honestly.
Sorry, come again?
I said I took CS101 and CS102 a long time ago, and I don't remember actually about this.
Okay. So CS101, we studied this thing. It's part of your material. If you say system.current time in milliseconds, it's going to give you a long value. That's a current time. If I want to find how long did the program take, what we can do is we can, when the program starts, we can call this method. Okay, make this call. It's going to give you a value. We store this in start. And then you go and run your program. Whenever your program finishes, we're going to repeat the same thing. We're going to say long now equals this. Okay, and then you can subtract this value from that value. So now my start is going to give you the difference of the time. That's actually the time taken by a program. And you can divide it by 1000 to get the time in seconds. Because this is giving in milliseconds. So if you divide it by 1000, that's going to give you in seconds. Okay, moving on. Let's look at these two codes. They're essentially doing the same thing, but the code is different. So the first method, the one on the top, is public static string repeat 1. It's taking 2 parameters. It takes character C and integer n. Now, we build a dummy string called answer. Okay, there's nothing inside it in the beginning. And we run a loop. The loop is going to run from 0 to n. Remember, n is provided as a parameter. So we're simply running the loop n times, whatever the value of n. And inside the loop, what we're doing is we're saying answer equals answer plus c. So basically, we're building a string. So imagine if the character is 1, okay? The character is 1, I pass 1 as character. And I give integer n, let's say 3. This means the loop is going to run 3 times. And my string is within the code is going to be 1, 1, 1. Okay? It's a very simple program. It's just building a string based on the data provided. All right. If you look at the second program, okay, same number of parameters. This time we're using a library. We're using string builder SB equals new string builder. Okay, and again we're repeating the same code as before. Run the loop from 0 to n, and inside this we're doing sb.append. sb.append. SB is the object of string builder, and we're appending the character C within this. Once the loop is finished, we're going to convert this SB object to a string, and return the string. So the inputs are exactly the same. The output is exactly the same. This is returning the string, this is returning the string, but the internal logic is different. Okay? Internal logic is different. Now, I'm going to run these two programs. I'm going to show you some results. When I run it on my computer, these are my results. This is what I get. So if the size of n is 50,000, okay, the first program took 2,884 milliseconds. The second program took only 1 millisecond. Look at a very large value. When n is very large, it's taking so many milliseconds. This is probably a few hours. And the second program took only 135 milliseconds. So what does that tell you? Both of these programs are very identical.
The second one is way more optimal.
Yeah, both of them have the exact same input, the exact same output, okay? But the internal logic is different. So this experiment is telling us that if you write your code properly, okay, you can optimize your program, you can make it work faster. Okay, second thing that we learn is, if you look at two programs, both of them are different solutions, okay? It does not mean that both solutions would have the same runtime. One solution can be better than the other solution. In reality, this happens all the time. Okay, this is just a comparison on the graph of the same data. Okay, so what we just did now is called experimental study. Experimental studies are scientific ways of validating a solution. Okay, nowadays we have the coronavirus issue. So far, nobody has come up with a vaccine. Why do you think making a vaccine takes such a long time? Anyone?
Because of the study, they have to test it first.
Yes. To come up with a vaccine that humans can use, okay, we have to test the vaccine first on other species. We go with rats, we go with other animals, rabbits, etc., before it goes for human consumption. So it takes time. That's one of the reasons it's taking such a long time to come up with a vaccine. So the problem with experimental studies is they are time intensive. Okay? So in computers, that's very easy because the job of the computer is to compute. Technically, if you have a good enough computer, you should be able to run any number of experimental studies. But that's not always the case. Let me show you why. Okay. These are some of the limitations for experimental studies. All right. The first limitation is if you just have an idea, okay, and you want to check if it is good enough, if it is fast enough, if this idea can be sold to customers and you can make money out of it, you first have to implement it. Okay? You have to write code, you have to spend a lot of time hiring programmers, software engineers, designers to build the application. Once the application is ready, okay, you will be able to sell it to people. But it requires a long time to build this application. Second thing, if you're doing this thing based on experimental validation, okay, it's not guaranteed that you're going to get the right results. Sometimes, if I build an application, it works fine on my computer. But if I give it to somebody else and they try to install it on their computer, it will probably give different results. Okay, so this also happens very often. Third thing is, if you want to be able to compare two different programs, okay, you have to make sure that you have the identical hardware. Why is this important?
Because the difference in like performance with other computers, let's say so older computer won't perform as good as a newer one.
Okay, very good. So yeah, it's a valid point. A newer computer would technically should be faster than an older computer. A computer with better specifications, like a better CPU, better RAM, better hard drive, should work faster compared to an older.
And sometimes the x80, sometimes it's x86 or x64, so sometimes there is difference. There's a lot of difference in hardware.
True, that's also something to do with the platform, if it is 32-bit or 64-bit platform. Yes, so these things are there. These are some things that make your experimental study very difficult to manage. Okay, so here are some of the challenges. It's hard to run two different or even similar programs on two different computers and expect different results. Okay, experimental studies can be done only with a limited set of test inputs. Like we do not know what kind of inputs would be provided by the users. That's why we always have the security issues. Whenever you install a new software on your computer or on your device, on your mobile phone or your tablet, whatever, okay, we're not sure how that application would perform on your device. I mean, it is possible that it can start stealing information, okay, like what many of the popular products are doing. Have you heard of Amazon's Alexa?
Yes. Yes.
Yeah, this device has a common problem, which is even if you're not using it, it's still recording your voice and sending it to Amazon servers. Same goes with Google. Okay, if you have synchronized the many different devices that you have using your Google account, Google is listening to everything. Same goes with your mobile phones. Your mobile phones, if you turn on the location, okay, the GPS location, it immediately starts sending information to somebody. Yeah, I'm not going to mention names, but yeah, there are people or organizations which are collecting all this information. Okay.
Doctor,
The third problem is the algorithm must be fully implemented before you can execute it to do an experimental study, which means that the whole process could be very expensive. And if I have an idea and I would like to just try it out, see if it is good enough, I have to invest a lot of money building the software, getting the right kind of hardware, okay, and making sure that the program works on all kinds of hardwares. So these are the main challenges and limitations for experimental studies. That's what experimental studies, okay, they're good, they're valid, but they're not fast enough. Okay, somebody was asking me a question. No questions, so we can go ahead. Okay, so now why are we studying this? Number one reason is we're going to talk about analysis of algorithms because we want to be able to compare two programs without actually doing experimental analysis, okay? Second thing is to do or apply the technique that we're going to learn right now, we don't have to have Java code for it, okay? If you just have an idea, you can just give me steps on how to do this. We can technically, mathematically, we can compare the two programs. And third thing is, it is possible to accept almost any kind of input. So you don't have to worry about the hardware or software. You don't have to worry about the size of the input or the output, okay? We don't even have to write code in any programming language. We just need an idea, a program, an algorithm. We can use mathematical analysis to determine the runtime or how long the program is going to take. Okay, so let's begin. Let's first talk about the running time. Now, I want you to focus on the graph in front of you. Let's say there was some program that I wrote and I wanted to run it on my computer. Fine. I'm going to run the same program with the same input, okay? The input is not changing. The input is exactly the same. And the output, of course, would be the same. Now, I'm going to run this program many number of times. And what I observe is, okay, the run times could be different. So the first time I run it, it took 5 milliseconds. Second time, it took 3 milliseconds. Third time, it took 4 milliseconds. Then 5 milliseconds. So what's going on? Has it ever happened to you?
Is it because of the cache inside the CPU, maybe? Like it's actually like memorized some of the instructions? I think, I'm not sure, to be honest.
Okay, good idea. Yes, you're getting in this way. Has it ever happened to you that you double click on an application, it took a long time to load, then you close it, then you double click on it again and it loaded very fast? Okay, and then you close it. The third time you load it, it was probably a bit slower. Okay, so this can happen because of the underlying condition of your system. So there can be many factors for this. But what we can say is, let's look at again at this graph. You can say that I ran this program, my program, 7, 8 times. Okay, and every time I'm just checking how long did it take to run the program. So you can see that the best possible time, the best case time was, for instance, E, which is about, let's say, 2.5 milliseconds. And the worst case time was 5 milliseconds. Okay? So when I'm going to sell this program, this product to my customers, and if somebody asks, hey, how long is it going to take? What should be my answer? Should I give him 2.5 milliseconds or 5 milliseconds?
Between 2 and 5.
Okay, if I say it's going to take 2.5 milliseconds, it's probably not true. Okay, when the client runs this program on his computer, that will probably take 5 milliseconds, so he's going to be upset with you. Okay, if you say the worst time, let's say you'll say 5 milliseconds, you're being honest. Okay, you're saying that the worst case scenario, I ran this program many times on my computer, and it never took more than 5 milliseconds. So we hope that when you run this on your program on your computer, it will take 5 milliseconds or less. So if you say something like this, that's a worst case time. Okay, your customer would be happy. Okay, you were honest. But what if your competitor sells the same program, saying that his program took 3 milliseconds? Okay, now you're going to lose to your customer, your competition. You're going to lose business. So what do companies do? If, let's say if I'm a company and I would like to have a software built for me, I'm going to go for software houses which construct software for companies, commercial software. So I'm going to ask them, hey, these 10 companies, I want you to go and build this software, and I want it to run in this much time. And then they're going to start bidding. They say, okay, we're going to pay you, or you will pay us this much amount of money, and we're going to build the software for you. Okay. Now, how would you determine which one is the best one? Of course, we're going to look at the cost, okay, money, and the second factor would be the time, reliability of the software. So naturally, we'll go for the cheapest one and the fastest one. Okay, but again, should we trust the worst case time, or should we trust the best case time? Or do we have to come up with something better? Let's say we come up with the average case time. What do you think?
Average case. Yeah.
Okay, average case, yes, average case would be much better. It would be more honest realization of your program. Now the problem is computing the average case could be different. Okay, it involves a little bit of mathematics, of course, the average formula, and then you have to do some more mathematical equations. All right, so what we do is we do theoretical analysis. We use a little bit of mathematics to try to determine the average case runtime from our program. Okay, that's our goal. We want to come up with the average case runtime for my program. All right, so some benefits of this is, okay, again, you don't have to worry about the code. You just need to have a very high level description of the algorithm. Second thing is the size of the input. We can always go with a very large value of input. We always say, okay, let's say size n. Size n means something which is very large, anything that is approaching almost infinity. Okay, we consider almost any kind of input. We're not going to worry about integers or doubles or arrays or linked lists or whatever data structure. We assume that everything is open and your program can handle any kind of input. Okay, and lastly, and the most importantly, we're going to assume the runtimes independent of the software and the hardware. Okay, we don't care about the underlying software, the operating system, the hardware. We're just going to give a mathematical notation, and you can use that mathematical notation to compare with other programs. Okay. Now, we'll try to understand some primitive operations, some basic operations that computers do. Okay, so these include evaluating an expression. For example, 2 plus 5, okay? 3 minus 2, 5 divided by 10, 2 times 3. So these are primitive operations, things that will take a constant amount of time, very small time, a time which could be almost negligible, almost close to 0. Okay, some other examples, assigning a variable. For example, I can say integer x equals to 2. Okay, it's going to take, let's say, 1 second to do this. 1 second is a very small time, or one operation is a very small time. All right, another example, indexing into an array, jumping to a value in the array. For example, I say, hey, I have an array, jump to position 3 in the array. So index jump into an array is also a constant operation. Okay, it's taking a constant amount of time, very small amount of time. Calling a method, returning something from the method. So all of these things are called Primitive operations, they are some things that we require to have. These are essential. These are easy to work with. They have very limited time frame, and usually they take a very little amount of space. Okay, so let's have a look at an example for how do you estimate primitive operations. Okay, do you guys see the code in front of you?
Yes, we can.
Okay, I have this code in front of you. I would like you to pay a lot of attention over here because we'll try to understand how estimation works. Okay, and this information is going to be very important for the rest of the class and even for the next week. All right, so on the last slide, I mentioned some of the primitive operations. Okay, let's look at this example. Just going to look at this code. Again, it doesn't have to be a code. It doesn't have to be Java. It can be even a simple algorithm with steps. But let's go with this since we are familiar with Java. So line number 1 is just a comment. Would that be executed by the processor?
No.
Yeah, no.
Yeah.
So we do not execute comments in your program. Now, line number 2 is a call to the method. So public static double array max, which is taking a parameter double array data. Okay, so on the last slide, I just said this thing. Calling a method, method definition, returning something from the method, all of these are primitive operations. So we can ignore this. We can say, okay, this is not going to take any time for my program, this particular program. Line number 3 is we're defining an integer. We're saying integer n. So defining an integer is considered as one operation. And now we're saying data.length. Can somebody tell me what is this data?
A class.
Array.
Very good. This is the array which is passed as a parameter. So what we're saying is go to the array and fetch the length of this array. Okay. Usually, where are the arrays stored? Are they in the memory? Or
yes. No,
they are variables. Anyone?
Yes, it will be in the memory.
Okay. Remember that I think even this week and last week we talked about static. What's the meaning of static?
I think every class can have the access to reach this class.
No, that's not static.
it means it's not changeable, or like it's not changing, it's constant.
No, again, I think you forgot. So if I define a method with the static keyword, this means before the program starts executing, it's going to check which methods have the static variable. So if this method has a static variable, what's going to happen is it's going to define the memory location for all the variables defined within this method. So look how many variables are defined. We have integer n, we have double current max, that's 2. We have integer day, that's 3. That's it, 3. So it's going to define the memory for these 3 before even the method starts. In other words, the memory is already available to you before the method begins. Now, if you do not define it static, okay, just remove this keyword. This means by default, this is dynamic, which means the operating system is going to look at this code and it will not do anything. It will not allocate any memory for this program, okay? When the program starts running, it will go and fetch the memory. It will ask the operating system, please give me 2 integers and 1 double. And the operating system will go and find this memory and assign this memory to this method. So which one is going to be faster, static or dynamic?
Static.
Yeah, static would be faster. Okay, the memory is already available. So because this method is static, okay, we can say this thing integer n was already there before we started. So this would be one operation. Still defining this would be equal to one operation. And we're saying data.length. Data is a array, okay, of type double. Did we define the array data, or was it defined somewhere else?
It's defined somewhere else, maybe.
It's defined somewhere else. Okay, somebody else is going to call this method, and they're going to pass the array to this method. Okay, so we don't have to worry about that. But to go and fetch this, okay, data.length, we need to
this
go.
is one operation.
We need to go and fetch this from the memory. That's going to take one operation. So fetching length is one operation, and storing this in a local variable called integer n, that's another operation. So that's 2. 1 plus 1 is 2. Okay, so line number 3 is 2 operations. All right, let's move on. Line number 4. Line number 4, we're saying double current max equals to data at position 0. So again, double current max, we're defining a new variable, so it's going to be one operation, primitive operation. And then we're saying data 0. Again, go fetch this from the memory. Fetch this from the memory. So we'll go and fetch it from the memory. This is going to be one operation. So this 2 operations again. Okay, so line number 4 is 2 operations. Let's look at line number 5. Line number 5 is saying for integer j equals 1, j is less than n, j plus plus. Now notice in a for loop, we have 3 statements here. So this is the definition of the counter. Okay, integer j equals 1. So again, defining j would be a primitive operation. Okay, that's going to count as one operation. Right, what if I put 1 in this? Should we count this as another operation? Notice what we did over here. We said integer n equals data.length, and we said this is equal to 2 operations.
Yes.
This also be 2 operations or just one operation?
I think it should be 1 because it's a constant number.
Okay.
There is no need to fetch the
very good.
Of the data.
There is no need to fetch 1. Okay, 1 is a literal. You just define it. We're assigning this to the local variable. So this counts as one operation. Now, this loop is going to be running based on this condition and the counter. Okay, so how many times are you going to check this? It depends on the value of n. It depends on the value of n. Do you know the value of n?
No.
Come on, you know this.
Yeah, we have it data.length.
Okay, but we do not know exactly what is the size of the array. It depends on whoever passed this array. We don't know. So what we can do is we can say, okay, let's consider n to be a very large value. We'll give it in terms of n. So let's say this particular condition is going to run n times. Okay, it's going to run n times. This is going to run n times. How about j++? How many times is this going to execute? 1 time?
Until we reach n.
Yes. So it's going to increment every time you get back over here. Okay, that's how loops work. So if this condition is true, we go inside, we finish all execution of these lines of code, then we come back and increment the counter. Then we go and check the condition again. If the condition is valid, we go inside again. So to tell you the truth, if this is running n time, this is also going to run n times. So far, so good? So if I'm looking at this line, okay, if I'm looking at this line, so integer j equals 1, this took 1 operation. J is less than n, runs n times. J++ also runs n times. Can I say that this is n plus n plus 1? Can I say this is 2n plus 1?
Yeah, but isn't 1 negligible because like n is a big number?
Yeah, of course n is negligible, but that's okay. Let's continue. So this would be 2n plus 1. Okay, let's look at this one, line number 6. So if data of j is bigger than current max, okay, current max. Right. Let's say data of j, where is it? Is it locally available, or do we have to go and fetch it?
You have to fetch it.
You have to fetch it. Okay, so this should be equal to 1 operation. this should be equal to 1 operation. Every time we have to go fetch it. Like, what about current max? Is it available locally?
Oh, yes.
Okay, you already defined it and you store the value inside. So it's a local value, it's literal, just like what we did with j equals to 1. Okay, so it's just a value. So we should not really count this as an operation. It's just a value. So now the third thing is comparison. Hey, this thing is bigger than this. Now comparing something is going to take some time. Okay, it could be very small time, but still it's taking time. So this is 2 operations now. All right, 1 operation is to go fetch the data from the array. Second operation is comparing this with the current max. So this is 2 operations. Okay.
But you wrote at line 6, it's 2 n operations. Is that like a mistake?
Now the thing is, this if condition is inside the for loop. Okay.
So
how many times does the for loop run?
n times.
N times. For loop is going to run n times. So whatever this is, we have to multiply it with n. So this was 2 operations. Okay.
Oh,
now, independent of the loop, we can say this is 2 n operations now. Okay. Line number 6 is 2 n operations. All right. Let's look at line number 7. Line number 7 is inside the for loop, and it's also inside the if condition. Okay, it's inside the for loop, and it's also inside the if condition. Right. Let's see how many times do we get over here. Depends on the if condition. If the if condition is true, we'll go and execute this line of code. If the if condition is false, we will not go there. Okay. Can we estimate how many times are we going to get over here? Can we estimate that correctly?
No, because it depends if it goes through or not.
Good. So yeah, we cannot estimate now. We do not know what the data is. We do not know what's the current max. Okay, we don't know. We don't have this information. So what we can do is we can look at the best case and the worst case. Remember a few seconds ago we talked about best case and worst case?
Yes.
So we can say the best case is, let's hope we never come here. Okay, this condition is always false and we never come over here. In this case, if I never come over here, the runtime would be 0 operations, 0 seconds. And the worst case scenario is this is always true, okay, and I always come over here. So we're gonna say something, the time for 7 would be something between 0 and the runtime for this one. Let's see what's the runtime for line number 7, independent of the if condition and the for loop. So here we're saying current max equals to data j. Okay, data j means go fetch the value and then store it in the local variable current max. So fetch and store, these are 2 operations. Okay, these are 2 operations. Now, because this is inside the for loop and the for loop is running n times, okay, so I can say this is 2n. The runtime for line number 7 would be either 0 or 2n operations. Okay, 2n operations. Now,
2n,
line number 8 is return current max. Is this inside the loop or outside?
It's inside.
Are you sure?
Is it? No, it is not.
That's not inside the loop. Okay.
Yeah.
I don't know if you studied with the curly braces or without the curly braces. If there's no scope defined for the loop, this means only the next line is inside the loop. Okay. As it happens, there's only one if condition, and the same goes over here. There is no scope defined over here, which means only one line inside the if condition. So this line is inside the if condition, and the if condition is inside the for loop. There's only one line. Consider all of this as one line. So bottom line is line number 8 is not in the if condition. They're simply saying return this. Now returning, okay, is equal to one operation. Returning is one operation. Okay, so can I add up all of these values? Can I add up all of these values and give it like an equation? Okay, let me try to do this now. So I'm going to take a screenshot.
Bro, this is like an introduction to the big O notation.
Yes,
It's very.
we're moving there.
Okay.
All right, so here's just a summary of what we did. Okay, so how many operations? So we don't count this one, we don't count this one. Why? This one is a comment. Okay, and this one is also not counted because this is the method definition. Okay, this one would be defined as a local variable. Okay, it's just a variable. If you like, you can consider this. If you don't want, that's fine. Okay, how many operations was this? So this was considered. This is one operation, and fetching from the array was one operation. So this was two operations. Okay, how about this one? Defining current max.
Two.
And then fetching.
Fetching this. So we consider this equal to two operations. The for loop, this was considered as one operation.
Yes.
Okay.
And then this.
But this one was running n times. This one. And
yeah,
this
so
one.
n times 2 is 2n.
N times and n times. So we can say this thing, this is n plus n. And we had the 1 before it. 1 was for the integer. Okay. Now, how about this one? We said this is one operation. And the comparison was the second operation. So this was two operations. Okay. But it needs to be multiplied with n.
With n.
Why n?
Because it will work n times.
Because this is inside the loop.
Yes.
Okay. How about this one? Line number 7.
From 0 to
fetching a value, and then we're storing it in the local variable. So we're considering this to be equal to 2n. Okay, two operations. And because this is inside the loop, so we're going to multiply it by n. Okay, so it's either this or
0.
Or 0. Okay, why 0?
Because the worst case scenario.
That would be the best case scenario, that we never come over here.
Yeah, best, okay.
Okay, and line number 8 is return the value. So returning is just one operation. Now, if I want to write this again as an equation, can I add it up? Can I say how many are integers? So we have 1, 2, 3, 4, 5, 6. Okay, and how many n variables? So this is 2n, 4n, 6n.
Yes, so 6n.
Okay, so it's either 6n plus 6 or okay, if you consider this 0.
Or n plus 1.
4n plus 2 plus 6.
4n plus 6. Okay, so it's either this or this. So I can say that, let's say the runtime for this program is tn. It's given by some equation tn. I can say that, okay, this goes within this bound. It can be 6n plus 6, 4 plus 6. Okay, so I can say that this is my average time. My average time is going to be between this value, 6n plus 6, and 4n plus 6. It cannot be any slower than this one, cannot be any faster than this one. Does it make sense now?
Yes.
Okay, so this is my equation. Okay, my mathematical notation. I can estimate easily by looking at the code how many operations would be there, and I can define it using an equation like this. All right, any question about this? Is this clear?
Yes, it's clear. Yes.
Yes, it's clear, Doctor.
Okay, good. Let's move on. All right. So this is information taken from the other textbook. Okay, it's just showing you some examples of experimental runtime for some of these operations. So you can see that we did these experiments on a MacBook Pro with 2.2 gigahertz processor and 2 GB RAM. Of course, it's an old computer. You can see some operations like add, multiply, divide. You can see how many nanoseconds they're taking. Nanoseconds is a very small time. Do you agree? It's like 1 billion.
10 to the power of -9.
Yes. So you can see that these operations are taking very small time. Even if you do 1 billion of them, it's still going to be just a second, maybe less than a second, or a bit more than a second. Okay. Now, there's something which is very important. Fetching something from the memory, okay? Fetching something from the memory may take more time. So let's assume that declaring a variable, of course, is going to take some memory. Let's assume that it's going to take some constant time C1. Okay, assignment operation, comparison, declaring an array element, accessing an array element, fetching the size of an array. All of these are some primitive operations or constant times. But sometimes going over repeatedly doing the constant time n number of times, okay, could be different. For example, look at 1D, single dimension array allocation. If I want to declare an array of size n and I want to go and copy values in the array, fill it up, okay?
Yeah.
So one value in the array, and let's say the size of the array is n. So I'll say it's going to take some constant time multiplied by n number of operations. Same goes with the 2D array. A 2D array, let's assume that it has n number of rows, n number of columns. So to put everything inside this array, it will take some constant time multiplied by n squared.
Yeah, just like the for loop we did. Now it's like 2 for loops.
Good observation. Okay, here's an example. Another example. Some code in front of you. Okay. So you can see the red one. If a of I equals 0. A of I means we want to fetch the value from the memory, and then we're going to compare it. We're going to compare it with 0. Okay, this is inside the loop. Can you estimate how long the loop is going to take? It's running from 0 until n. We can say that the loop is going to run n times.
Yes.
Which means if I look at if condition, okay, we're going to go and fetch the value from array n times.
Is it like the other one, like between 0 and n times?
Yes, of course. Between 0 and n. No, here we're saying this is inside the for loop, and you have to go and fetch this every time. The counter, on the other hand, okay, it depends on the condition. If the condition is true, we'll go and increment the counter. If it is false, we will not increment the counter. Okay, so for this one, this would depend. It will be between 0 to something else. But this one, this line is inside the for loop. That's going to run n time.
Yeah, I meant the count plus plus.
Okay, so far so good. Any questions?
No, Doctor, everything is clear.
Okay, great.
Doctor, when we have n squared, does that mean like we're increasing the time exponentially?
N squared? No. N squared is, yeah. Let's look at this now. We're going to talk about it now. So, okay, if there's no other questions, let's move on. Let's talk about some important functions, okay? This is not the end of the world. There's many other functions, but these are 7 classes of algorithms, okay? With polynomial time. We call them polynomial time runtimes. So let's try to learn these. The first one is called constant time, which means that you wrote a program and it's taking constant amount of time. This would be ideal because it's instantaneous, it's really fast, and nothing can be faster than a constant time algorithm. The second class is called logarithmic. Okay, this is log of n. So the growth function, okay, we call it the growth function, would be log of n. Third class is linear. Okay, that will be your typical for loop, which is going from 0 to n, linear time. Then we have a linear arithmetic, which is known as n log of n. Okay, n multiplied by log of n. Next is quadratic, which is n squared. Next is cubic, which is n cubed. And the worst of these, okay, the worst of these, which is the eighth one, okay, it is exponential. Exponential is usually not considered polynomial time. It's exponential time, which is a very large value. Okay, if you want to plot it, it's going to look like this. This is constant time. This is log time. Okay, you can see this thing in the beginning. It will jump very quickly. And then we have the linear time. We have the logarithmic time. Okay, and squared is quadratic time. And cube is cubic time. And finally, the exponential. It's growing really fast. So which one is the best one?
As in for the processor? The first one, the constant.
Constant.
Yeah, the constant is really good. Okay, but it rarely happens. We have log time.
It's only for like primitive types or something.
Log time is really good. If you can get that, this is very good. Okay, linear is okay. Right. So far, we've studied only one data structure, which is linked list. We look at 3 different variations. Okay, we looked at the circular linked list, single linked list, and double linked list. Right, I'm going to ask you very quickly, and you're going to give me an answer. If I want to search a value inside the singular linked list, how long would it take? Assume the size of the linked list is n.
Dn equals to n.
Okay, if there's n nodes, if I'm searching for a value, okay, I do not know exactly where the value is. It can be in the beginning, it can be somewhere in the middle of the list, it can be somewhere at the end. Okay, if it is in the beginning, I may get some constant time, maybe 1, 2, 3, 4, 10, 100, 1000 operations, and then I'll find my value. So the runtime would be constant. But imagine it is the last value, the last value of the list. So this means I have to go over all the list until I find my value. So in this case, the runtime would be n. Okay, so we can say that the best case scenario for searching a value in a linked list would be constant time. The worst case scenario is
linear
time. Okay, linear time. All right, moving on. These are some common functions and some examples. Now, this is just giving you a rule of thumb idea. If some code is given to you, how you can estimate the runtime for it. If I have an expression like this, A equals B plus C, okay, this is constant time. We know this is 2, 3 operations. 2, 3 operations is just constant time. If you have a loop like this, okay, and the loop is incrementing by the order of 2, or sorry, dividing by the order of 2. So n equals n divided by 2. And every time we divide the counter by 2. If you have something like this, you're going to get log of n time. Okay, this is very important. Later on, we're going to study some algorithms which are log n time, and the property would be that you have to divide the counter by 2 every time, in every iteration.
Is it only by 2, or like it could be other numbers?
Okay, 2 is very important because in computers we go by log of 2. So this is not actually log base 10. This is log base 10. All right. Linear would be simple. We just saw this thing in the previous example. So going something from 0 to n, and you're incrementing it by 1 every time. So this is linear. Okay. Linear arithmetic naturally would be, okay, you can put these two together. If you put this loop in the other loop, you're going to get this. Later on, we're going to talk about these extensively when we study the sorting algorithms in week number 6 and 7. Okay, we have quadratic. It's very simple to look at it. You should have two loops like this, two nested loops. The first loop and the second loop, both of them run n times. Okay, cubic would be 3 loops. All right, like this, 3 loops. Each one is running n times. So eventually you're going to have a cubic time. An exponential, okay, we're going to see other examples later on. One example is combinatorial search, okay, exhaustive search. This is exponential time. All right, so if you're, as a programmer, as a software engineer, if you can come up with a solution that runs in constant time, log time, linear time, even linear arithmetic time, your program is good enough, okay? Quadratic is not good. It's usually slow. Cubic is worse, and exponential is something that we'll try to avoid at every cost. So far, so good?
Yes.
Okay. Log n is logarithmic function, and that is also considered a good time. X1 is linear time. Okay, then we have logarithmetic, which is n log of n. You can simply call it n log of n. Then we have quadratic, which is n squared. We have cubic, n cubed, and then finally exponential, 2n, 2 to the power n. So out of these functions, which one is the first one?
Which one is
The
what?
fastest is the constant, and the one that takes time the longest is exponential.
Okay, good. So the fastest one is the constant, and the one that takes the most amount of time is exponential. So then the computer science students, they will study these in more detail in the next course, which is called Algorithms, CS210. In that course, they're going to talk about other functions. But here, because this is just an introduction to this topic, and probably this is the first time you're hearing about these, so let's only work with these functions, the ones that are available in front of you. So, of course, the fastest one is constant time. That would be the fastest possible algorithm, but it's not possible to have solutions with constant runtimes. Okay, so if I look at the first six functions in this order, you're going to remove the exponential from there. So first 6 functions are also known as P functions, or they can be done in polynomial time functions. The last one is exponential. Exponential is not part of the polynomial type class, okay? That takes more time than a polynomial function. I believe you know about polynomials. You studied this in mathematics.
Yes.
Okay. I believe somebody started recording the lecture. That's okay. That's good. So here is just a graphical representation of the same functions. All right. So I can say g of n equals 1. This is constant. Yes, question?
Do you know if the course algorithms is in also software engineering? Because I'm taking software engineering, not computer science.
Okay, for software engineering students, algorithms is not a required course. Okay, but you're strongly recommended to take it as a elective. Software engineering students have 4 electives, 4 SE electives. They can take this as an elective.
Okay.
So this one is constant. This one, of course, is log of n. This is linear. This is linear arithmetic, quadratic, cubic, and exponential. Okay. So I believe I showed you this slide, and this is where we stopped last week. So these are some examples. If you have some code, you can look at the code and you can quickly estimate the runtime. if you have an expression like this, A equals B plus C, or A equals 10, okay, something of this sort, so the runtime for this one is going to be constant. If you have a loop, okay, if you have a loop that goes from 1 to n, again, if you have a loop that goes from 1 to n, but the incrementing function is always dividing by 2, okay, if the incrementing function is always dividing by 2, yani the loop is going to, the space for the loop is going to become half, and then half, and then half in every single iteration, then the runtime would be log of n. If this is a simple loop which goes from 1 to n or 0 to n, okay, with a increment function of +1 or -1, then the runtime would be linear. Okay, if you merge these two together in one loop, for example, I'll put this loop inside this loop, or this loop inside the other loop, then you're going to get n log of n. We'll talk about this in more detail when we studied the sorting in the last week. We also have the quadratic function. Quadratic is 2 loops nested together like this. So the first loop is going from 0 to n or 1 to n. The second loop is also with the same space. So this would be a quadratic n squared, which means the statement over here, whatever is here, is going to run exactly n squared times. Cubic, same thing with 3 loops. Okay, so first loop, second loop, and the third loop. And the statement over here is basically going to run or execute n cubed times. All right, exponential, okay, you can put all of this, okay, in another loop or in another loop, so n number of loops, you're going to get something which is exponential. All right, now let's come to the topic of estimating the runtimes. So remember when we started studying about this topic, we said that to be able to exactly know the runtime, what you have to do is you have to write the code, you have to compile and run the code on a particular platform, hardware and software, and then we're going to record the times. Okay, so that will be called an empirical evaluation. We're doing an experimental study and we're recording the time for every time you run the program. Now, it is possible that if you run the program many number of times, sometimes the program would run faster than the other times. So this is how we get the worst case time and we get the best case time. So for example, if I have a program and I run it on my computer 10 times, okay, so out of all of these 10 times, let's say one time it ran the fastest. So that will be the best case time. And out of all of these 10 times, it worked the slowest. So that will be worst case time. Now, estimating, okay, based on the best case time is not a very good idea. Because again, if I sell my software or my product to a customer telling him that, hey, my program runs in this much time, which is the best case time. And when he goes and runs the program on his platform, on his computer, okay, he's going to be disappointed because it may run slower. The second thing is giving him the worst case time. If you give him the worst case time, okay, that's being honest with the customer. But on the other hand, you can lose to your competition because your competition may say, oh, my program works faster than your program. So to be exact, the best solution is we have to give them the average case time. But finding the average case time is not easy. Okay? For example, let's say I ran the program 10 times and I calculate the average time. And then when I'm selling my product, I'm going to say, okay, my program runs in this average time. But when this customer goes and runs it on his computer, it could be different. Okay? Maybe he's not going to get the average case time. Maybe he's going to get something faster or perhaps even slower than that. So average case, okay, in its sense, is not stationary and you can change. Every time you're going to run the program again, the average will change. Let's say I ran the program the 11th time, my average will change. I ran the program the 12th time, the average will change. So it's very difficult to estimate the average runtime. Okay, I'm not saying it's not possible, because you're going to study this in the next course, how to do that. So what we can do is we can estimate this based on two scenarios. We can say that my program can run, my program can run in a best case scenario and a worst case scenario. I can say that I don't have to go and compute the average case. I'll simply say that my program runs between this interval. Okay, it runs between this interval. So I'm going to give the best case and the worst case. And I can expect my customer to understand that the best case is this and the worst case is this, and your program should run between this interval, between the best and the worst. Yeah, somebody had a question?
Yes, Doctor. I think we learned in stat that to get maybe a more accurate average, maybe we will need to have at least 50 samples to get a good normal distribution.
Very good, very good. So yeah, so you're talking about maths now. Indeed, yes, this is the essence of experimental study. So you have to repeat the experiment a certain number of times before you can give this. Okay, the best way of doing this thing is using some stat functions like P function or R function or T function or T stat. So again, these are different methods that we use for these things. You're going to learn this in the next future course. Okay, so far so good. So what this slide is telling you is you don't have to actually go and measure the average case runtime, because that requires a bit more statistics. Okay, so here what we're saying is we're only going to find the best case, we're going to find the worst case, and then we're going to give the average case as something between the best case and the worst case. So for example, let's say there's some program which runs in time t, okay? Runs in time t. So we're saying that if I run the program, my best case turned out to be this equation, 4n plus 5. And the worst case time was 5n plus 5. This means that on average, my program should be able to run between this interval. So this was the best case and this was the worst case. Okay. All right. Now remember one thing, I've said this before, I'm going to say this thing again. Experimental evaluation is not always perfect. Okay, there are many, many different parameters. For example, if you're doing experimental evaluation on two different computers, we have to be sure that the hardware exactly is the same. If there is a difference in the hardware, it's not going to work well. Second thing, even if the hardware is exactly the same, we also have to look at the platform. For example, on the first computer, you were using Windows 10, and the other computer, you were using Ubuntu or Mac OS or whatever. It doesn't work this way. Okay, both of the platforms must be the same. Okay. Third thing, we're going to see even if the platforms are the same, we need to know the situation, okay, on how many softwares are running in the background, how many processes are executing. We have to be sure about this. Both of the system state must be stable. On both computers, it should be identical. So doing these things is not easy. Okay. So what we can do is we can try to learn how order of growth works. Okay. Here's this, what you see in front of you is just a table. It's showing you runtimes for certain programs, okay? And it's telling you, so we have rows and we have columns. So the row is telling you the runtime, let's say for some program is log of n, C log of n. C is some constant time. So constant times log of n. If I want to run the same program for n plus 1 time, okay, it's going to be like this, log of n plus 1. If I want to run it 2n times, okay, I'm increasing the size of n. Let's say the size of the array was 1000. I'm simply doubling it. So in this case, the runtime would be this. Okay, if I increase the value of n to 4n, okay, the runtime would be something like this. Okay, look at the constant function. Let's say there was another program whose runtime is constant. So in this case, the runtime for n+1 would be like this. Okay, for 2n would be like this, 2cn. For 4n would be 4cn. So you can see this thing. It's not having a big impact. There's not a big difference between the original runtime, and even if you run the program more times, more number of times. So it's 4cn. Okay, but as this grows bigger, okay, you'll see that there's a big difference now. Look at a bigger number. Go with cn squared. Okay, substitute n+1 in n squared, and you're going to get something like this. If you put 2n in there, you're going to get something like this, 4cn squared. Okay, for 4n, it becomes 16cn squared. Look at the cube. Okay, 64cn cubed. So you see, just changing the size of the data by a little, okay, small number, is having an impact on the overall runtime. Okay, and the worst one, look at the worst one, which is exponential time. Okay, even if you put just one more value, n+1, you're going to get to the power n+1, which would be a big difference. Okay, but for a larger value like 4n, look what happens. C to the power 4n. This is going to be significantly larger than the original value over here. So this is just to explain that when your runtime of a program is in a bigger class, like n squared or n cubed or exponential, okay, even if you increase the size of your data by a little bit, is going to make your program really, really slow. Okay, but for smaller, for easier, for faster programs, it does not have a very big impact. Okay, here's another example, an explanation of the same thing. So imagine, okay, before this, have you guys heard of Moore's Law? Anyone?
Yes, I've heard of it.
What is Moore's Law?
It says that transistor will double every 2 years, and something like that. And we have almost reached the limit because of the size of the transistor itself.
Yeah, so Moore's Law, okay, in simple terms, just to make life easier for everybody to understand, it's saying that by the passage of time, every year, okay, because of innovation in technology, the size of the chipset will become smaller and smaller and smaller. Okay, this was said many, many, many years ago, and it's still holding true even to this day. So here what we're trying to say is in 1970s, we had very old technology. We didn't have ICs, okay? But nowadays in 2000, 2010s, 2020s, we have newer technology, embedded system. We have the whole computer on just one chip. Okay, in the 1970s, we didn't have something like this. So if you look at the order of growth for these functions, you can see that for a linear, let's say your program is running in linear time, in the 1970s, because of the hardware available, you would be able to run, let's say, 1 million instructions on that processor. Okay, with the improvement of technology, now you can run billions of instructions for that program. This is for linear. But if you look at bigger functions, okay, you can still see this thing, even with the improvement of hardware, okay? Imagine in 1970s, the kind of computers we had, and nowadays your processor, the processor in your smartwatch is faster than the supercomputer of 1970s. Okay, so even if you have a function, if you have a program that works in this, okay, there won't be a big difference on the impact of hardware improvement. So in the 1970s, if the computer was able to process only 100 instructions, nowadays it will be only 1,000 instructions. All right, this is really interesting. The last one is exponential. So imagine if you have a program that runs in exponential time. Okay, on a 1970s computer, it would have taken, let's say, 20 seconds. Okay, or let's say 20 instructions. It would be able to do only 20 instructions. But now with all the hardware improvements that you have, it still is taking only 30 instructions. So it's not a big difference. So we will see this thing later on. Things will become more clear when we start talking about the other data structures. Okay, so what we're trying to say over here is the impact of the hardware, okay, does not have a huge benefit. If you go and buy a supercomputer to run a stupid program, okay, the program will still run slow. But if you write an intelligent program, okay, if you write an intelligent program with a lower growth rate function, you can even run it faster, okay, on a small device like a smartwatch or a mobile phone, compared to a stupid program on a supercomputer.
Doctor, I realized something like that. I'm not sure if it's the same, but I've used a program that has been made in 2004, and my device is fairly new and it's really fast. Even though it's new and fast, it was still not, really fast. It was lagging and it wasn't working well. Does it have something similar to this, or is it something else?
Perhaps it is the similar thing. Perhaps I'm not exactly sure. We have to dissect the program itself, but there are some problems. Okay, for example, scheduling. We would like to schedule all the courses for all the students in Prince Sultan University. Okay, so you can look at the different parameters we have. We have number of students, we have number of teachers, we have number of classrooms, we have number of buildings. So all of these are different parameters. Now we have to see what is the best possible way of scheduling all the courses in the university. Okay, so this kind of problem is a non-polynomial time problem. Its runtime is something here between these two. So if you want to find a solution for this problem, okay, let's say I buy a supercomputer to find a solution for this problem, it's still going to take a massive amount of time to find a solution, because the problem itself needs to be written in a better way. It needs to be defined in a better way. So don't worry about it. If you're not exactly following what I'm doing, that's okay. As we grow, okay, as we go through the different content in this course, we're going to see what's going on, and things will be more clear to you. Okay, here's another example of the same thing. Okay, so this is a table for these growth functions. I'm just going to show you 2 or 3 things here. So let's say I have a program, its runtime is in N. It's a linear. In the 1970s, if I run it on a computer, I would be able to do, let's say, 1 million entry data, okay, or 1 million entries in, let's say, in 1 minute, let's say. On today's hardware, if I run the same program, it would be able to do it 1,000 times faster, okay, 1,000 times faster. All right, if I fix the data, if I run the same data on a 1970s computer, it will probably take a few minutes. If I do it on my computer nowadays, a new computer, okay, it will run really fast. I'm not sure if anybody's a fan of running old software on the computers. Do you guys play games, computer games, old computer games?
Like MS-DOS games?
Okay, yes, MS-DOS games. So games from the 1980s and 1990s. So if you try to run them on your computer nowadays, okay, it's not going to function very well because the speed of the processor has increased significantly.
It runs very much fast,
so your program, your game is going to run really fast and you won't be able to play it. All right. Now, if you look at a program which is really slow, which takes a long time, in the 1970s, when you try to do or try to execute it on a supercomputer, you won't have been able to find a solution for that. Okay, the computer will just keep working and never find a solution. But with nowadays technology, you will be able to do this thing in a millennia. Do you know what's a millennia? Anyone?
No.
100 years,
Milliseconds.
maybe.
Millennia is like 1,000 years.
1,000.
1,000 years. We're not talking about months or years. It's 1,000 years. Okay. So this tells us something, that as a software engineer, as a code developer, okay, as somebody who's playing with building programs or finding solutions for the customers, we have to invest more time in finding solutions, okay, which run faster. All right. Now I'm going to show you a practical experiment. So I have two programs. Both of them are doing the exact same thing. Both of them sort the data. So let's say I'm going to give an array of size 1,000. I would like these programs to sort the arrays in the same order, let's say ascending order. So one program is a bit slower. Its runtime is n squared. Okay, this is the quadratic class. And the other program's runtime is n log of n. Which one is faster, n squared or n log of n?
N log of n.
I'm not sure to be honest. Is it the schedule?
Log of n.
Come on, we saw this thing a few minutes ago. I showed you this slide. Remember this one? This is the order. So the fastest is constant, then you have log, linear, n log of n, n squared, n cubed, and the worst one is exponential. Okay, so I'm coming back over here. Right, so the first one is running in n squared time, the second one is running in n log of n time. So theoretically speaking, when you look at the numbers, this one runs faster. The merge sort is theoretically faster than the insertion sort. Okay, now let's say what happens. When I start running the program, okay, this is the runtime, and this is the number of elements, the size of my array. So if my array is really small, I'm talking about size 50, okay, size 50, you can see this, that the insertion sort, even though it's slower, theoretically speaking, experimentally, it works faster. Okay? But if you increase the size of the data, if you increase the number of elements, let's say make it 150. So you can see this thing, the runtime for insertion sort becomes slower compared to the merge sort, which is n log of n. They've increased this thing, scaled this graph to 2,000. Okay? This line will go like this, and this line goes up like that. Okay, so after a while, you'll realize that the insertion sort is really slow compared to merge sort. By the way, this was a project we gave to the students who took this class in the last semester. We asked them to run different sorting algorithms on a large data and compute the time. That was very interesting. Okay. All right. Now, remember one thing. The constant factors do not really affect the runtime. Okay? For example, here's a plot for this function. N plus this. This appears as a very big number. 10 to the power 2 is, of course, 100. 10 to the power 5 is how much? 100,000. Okay? So we're saying 100n plus 100,000. This still is a linear function. Still is a linear function because the value which is changing is the value of n. So if this is linear, okay, even if I increase it significantly in the constant terms, it's not going to have an impact over a long period of time. So even if I increase the value of n to a very large value, it's not going to have a significant impact. But compare this to a n squared function, a quadratic function. Okay, compare this to the quadratic function. Here we're doing the same thing. So 10 to the power 5 n squared plus 10 to the power 8 n, and so on. So again, remember this. the constant values which appear before a function itself. So for example, 10 to the power 5, 10 to the power 8, before the function itself, okay, they have an impact, but it's not a very big impact on the on the growth function itself. So in other words, today, later on, when we study the big O notation, we'll see that we can easily ignore these constant terms. All right.
Doctor?
Yes?
I'm not sure what the constant terms were in the previous formula.
Okay, let me go back. I'll show you the slide over here. Remember this one?
Yes.
Okay, so let's say this is some function. So 4n plus 5 is a runtime for some program, let's say. Yes. What we're saying is, even if you remove 4, okay, it's not going to have a very big impact. It's not going to have a very big impact. Why? Because the value of n is unknown. We don't know.
Okay.
N is usually the size of the data. So let's say we don't know. Okay, can be very small, can be a few numbers, can be millions, billions, trillions, we don't really know. Can be close to infinity. So what we're saying is, even if you remove the constant term like plus 5, okay?
Yes.
So let's say n is 1 million. So 4 million plus 5, 5 is nothing compared to it. So you can ignore the constant term. That's what we're saying.
Okay, thank you.
Same thing goes here, 5n plus 5. If n is a billion, what's a 5 billion plus 5? 5 is nothing compared to it.
Yes.
Same goes here. When you look at this one, what I just showed you over here, okay? This one has a huge impact. If I say 100n, and if I remove this one before n, there's a big difference.
Yes.
Let's say n is 1 million. So this one is going to become 100 million. That's a big difference. But this one itself is just a constant value. It doesn't change. You can ignore it.
So
okay?
1 and plus a million is nothing. It's the same.
Sorry? Yeah.
If the constant is 1 or a million, it's the same.
Oh, yes. So here, okay, 10 squared n, or 10 to the power 5n squared. This one is going to have a big impact.
Yes.
But this one has no impact because it's not changing. It's just constant.
Right, yes.
So you can, even if the number is very big and it's not changing, okay, you can ignore it. All right. Now, here's a definition. Let's look at the formal definition. Now, we're going to look at the big O notation. Like, we use 3 different notations to represent a runtime function because it's very difficult to find average time, like I just told you. Okay, so we can use 3 different functions or 3 different notations. First one is called a big O notation. Big O notation. This is how we define it. Here's a formal definition. Given functions f of n and g of n, we say that function f of n is big O of g of n if there are positive constants c and n naught such that this equation can be satisfied. So function f of n is less than or equal to constant c times g of n. Okay, we can satisfy this function if we substitute for n a constant value or some value n naught. All right. So this is the formal definition. Now what it means, here's an example. Let's say I have this function 2n plus 10. Okay, let's say this is some function f of n. We want to say that this is big O of n. We want to say that this is big O of n. So according to the definition over here, okay, this would be my f of n, and this would be my g of n. So far, so good? So this one is f of n, and this one is g of n, according to this definition. So what we're going to do is we're going to satisfy this. We're going to just rewrite it. So I'm going to write f of n. My f of n is 2n plus 10 over here. Okay, it's less than or equal to c, some constant. We don't know what's the value of this constant. Some c constant multiplied by g of n. So here g of n is simply n. So this is my equation. Now what we'll try to do is we'll try to solve it. Okay, mathematically, simple algebra. So if I try to solve it, I'm going to get something like this. Okay, I'm trying to solve it for n, so I'm going to get n is bigger than or equal to 10 over c minus 2. And to satisfy this equation, to make it true, okay, we have the luxury to pick any value for c. Any value for c and n naught that satisfies this. So if this can be satisfied by any of these two values, okay, we can say that this is true. We can say that the equation 2 of n plus 10 is big O of n. Is this clear, or should I explain it on the Jamboard?
There's something not clear for me. I didn't get what n is bigger or equal than NFO. I don't know what that means.
Okay,
And doctor, if it's 2, then it would be like 10 over 0, and it's like a special case. So does it matter, or like do we just like do whatever is like good for the equation?
No. Okay. Of course, we don't have this luxury. So what I'm going to do is I'm just going to rewrite this equation over here and try to explain it. So let's say there was some function. So we wrote some program, and its the runtime is given by 2n plus, what was it, 10? Yes. 2n plus 10. Okay.
And then O of n.
So what we're trying to prove is that f of n is big O of n. Okay, this belongs to the class linear, big O of n, linear class. Remember the different classes. The
yes.
Constant.
O of c and then O of n.
And then we have log of n. Okay, and then we have n
squared.
Linear.
And then n squared.
And log of n. Okay, and then we have n squared and n cubed. And finally, exponential. So these are the 7 functions that we've studied, order of growth functions. So somebody's saying, hey, this is the program, prove that this is big O of n. Big O of n. So what we're going to do is, according to the definition, what we saw over here. Okay, we're going to see that function of n is less than or equal to constant value times the g of n. So here, my g of n is n. Okay, it's given to you. So I'm going to rewrite it. I'm going to say a function of n is less than or equal to some constant multiplied by g of n. Okay, let's substitute the values. We're going to get 2n plus 10 less than or equal to c times n, because g of n is n. Now we'll try to solve it for n. Okay, so do it like this. 10 is less than or equal to c n minus 2n. Do you agree with this?
And then n outside.
Okay, and then let's try to do this. We have n outside, we can have n minus 2, sorry, c minus 2. And if you divide both sides by c minus 2, I get this.
Doctor, is this like the formula? Does it have a name? Or like, is it like a rule or something?
What formula? No, this is the formula. This is the formula given to you. So
no, like as in fn is less than or equal c of g of n. Is this like a rule or something?
This is the, yes, of course.
What is it called?
This is the definition of the big O notation.
Okay.
Okay, big O notation. You can call it the big O notation.
So the definition.
So we get this. Okay. Now what we need to do is to say that this is true. We have to find a value of c and n that satisfies this condition. Okay, that satisfies this. So let's say if I pick c to be 3, let's say c is 3. Okay, let's say c is 3, and n is, let's say, 11. Let's say. So if I substitute in this, I'm going to get 10 over 3 minus 2 is less than or equal to 11. If you look at it, 10 is less than or equal to 11. Does that hold? Is this true? 11 is bigger than or equal to 10. True?
Yes.
Yes. So we can say this thing. For these values of C, when C is 3 and n is 11, this is true. I can say that the function f of n is big O of n.
Mm-hmm.
Is that clear now?
But can we choose like whatever for the C?
Yes, you can choose whatever for the C. Okay, pick something else. Let's say C is 4 and n is equal to what? The only thing we have to do is we have to prove that this is true.
Mm.
Okay, so 10 over, so 4 minus 2. Okay, I can pick 6.
Okay.
So if you solve it, you're going to get 10 over 2 less than or equal to 6. So there'll be 5 less than or equal to 6. So, okay, this also
Okay.
works.
So whenever we get the, like if we get an answer, then it's true. It doesn't matter if like there's a situation where it's not true.
Yes, so that's what we're trying to do. And we have to find, let's see, this method is called proof-of induction, if I'm mentioning it correctly. So what we're trying to do is reason, come up with a value, and say that this function works with these values. It does not mean that it may work with all the values. What if C is 2? Would that work?
No, it would be 10 over 0 and then
10 over 0 is infinity, which is wrong.
Yep.
Okay, so it works with C is bigger than 2, okay, and for some value of n. But this has to be true. Again, it cannot also be negative because we're talking about time. Okay, time cannot be negative, so you should not have a negative value.
Hey, doctor, all these functions can be proven, right?
All functions can be proven, yes. Let's have a look at a few more examples. Okay, here's another example. Prove that n squared is not big O of n. Okay, how does that work?
do the same thing.
We'll do the exact same thing. You're saying some function, some program, its runtime is n squared. And we want to prove that this is big O of n. So here's my g of n. I'm going to
So generally it's big O of n squared, right?
It should be equal to c g of n. Okay, so if you substitute the value, you're going to get n squared less than c and n. You try to solve it for n, divide both sides by n, you're going to get n is less than or equal to c. So c is a constant term, it's not changing, but n could change. So this does not work at all. Okay, so if you provide a value for c, then n must be exactly the same value, but that's not true, it cannot happen. So we can say that this is wrong. Okay, it does not satisfy the condition. Another example. Let's try to do this one. Okay, so f of n is 7n minus 2. Prove it is big O of n. Okay, so again, what should we do? Same thing. F of n is less than or equal to c g of n. Okay, so simply substitute the value. C times n. Okay, let's try to solve this. So what I'll do is I'll flip these values. So I'm going to have 7n minus cn is less than or equal to 2. Is that okay? Does it make sense? I brought 2 on the other side and cn went to the other side.
Mm-hmm.
So I can write c7 minus c n less than or equal to 2. This is a constant term, so you can take it to the other side. And it's less than or equal to 2 over 7 minus c. Okay, so let's try to prove it. Which value would this work with?
More than 7.
Okay, n should be 1.
C should be more than 7.
C should be more than 7 or less than 7? How about 6?
I mean, it could be both ways, so.
So
Oh wait, actually no,
It will
yeah,
be
'cause
negative
it's minus
if
c.
it's more than 7.
Yeah, we don't want to have negative value because time cannot be negative.
Mm.
So it would work for this.
Yes.
So this would be 2/1. So 2 is bigger than or equal to 1 if we substitute the value of n to be 1. Okay? So it works for this. I can say this for n not equals 1 and c equals c. This function is big O of n.
But doctor, I don't get it. Like, do we need to just like put random numbers and then like it just works and then that's it?
See, the idea is that every program has to have a bound. So this is the best case scenario, and this is the worst case scenario. What you're trying to look for is something between this.
Okay.
Okay. So what we're saying is big O of n is something close to the worst case. Something close to this. But in essence, it should be within this bound, from here to here.
So can we use the big O notation to like find the best and the worst case scenarios?
No, big O is used to find something close to or proximate to worst case scenario. Almost always like this. We look for the largest possible value, and we say this program in the worst case scenario would run in this time, big O of n time. We have other functions which give you this. I'll talk about it later today. So other functions which talk about this. Okay. Can you find another value which satisfies this? Can we try to do this thing?
5.
5? C is 5. Okay, and n?
0 or 1.
So still be 1?
Yeah, n is 1.
This also works. Okay, anything else?
N 0 and then C4.
N equals 0 and C is 4. Yeah, this also works. Okay, so what we're trying to say is this works for these values. This works for these values. But what if you pick a different value? What if n is large? Let's say n is 1,000 or 100. Would that work? For this
No.
No, it won't.
C has to be bigger than 100.
No,
So
if C
I mean not bigger as like
to
negative
7,
100.
If you pick something like 6.99999, something like this, would that work?
Yes, it would.
Yeah,
So
because it
divide
would be
2 divided by 7, so 0.0000, so something which is small.
I tried it, doctor, with 6.999, and I got the left side, right side equal to 2,000.
Yeah, so as long as the right side is bigger than the left side, it's okay. So this may also work. Okay. Again, it's just a hit-and-run trial. What we're trying to do is we're just trying to prove that this is big O of n. And it can be done by, if you can pick 2 random values of n and c, as long as they satisfy the condition. And that's it. Your job is done.
But doctor, wouldn't the program, round the C to 7?
No. See, this is not about programming. So remember in the beginning of this lecture, I told you we want to have some mechanism which is independent of the computer. We don't have to worry about the code. We don't have to worry about the computer, the hardware, the software. It's just mathematics. So we're just estimating. We're estimating the runtime of the program. So don't worry about it that it's going to be divided by 6.999. No, it's just an estimate for us.
So, Doctor, if we have a formula, we can get the big O notation of the formula, right? Like we can, I don't know, like for example, if we have A n minus C, and then we can get the big O notation.
Where are you getting this from?
A function. From, for example, a program you did.
Yes, this is coming from the program. Okay? This is coming from the program. So somebody says, prove that the runtime for this one is one of those 7 classes that we studied. Okay, these are the 7 different classes that we studied. So which one is it? Okay,
it's
which
the
one is
O of n.
So just by looking at it, we can say, hey, this is big O of n. But then
Yes.
say, okay, prove it. Prove that this is big O of n. So this is
Then
how
you do the definition. Okay.
Okay, let's do more practice.
Doctor, what if we pick an invalid values?
Oh yeah, of course. If you pick an invalid value, it's not going to work. For example, pick n equals 2 and c equals 1. Is that going to work?
No.
N equals 2 and c equals 1. So 2 over 6. That's going to give you 1 over 3. 1 over 3 is bigger than 2? No, it doesn't work. So this is invalid.
Doctor?
Yeah.
How I can choose the end node? Like, how I can choose the numbers? Which numbers I can choose for the end node?
What do you mean end node? You're talking about this one? End node?
Yes, yes. Sorry, end node.
Yeah. So again, it's a bit of a hit and trial. Okay, but you can estimate this from the equation. If you have an equation like this, we can see this is 2. So you have to pick a c which is close to 7. So when you subtract it, overall is going to give you a larger value compared to this one.
Yeah.
So you can notice what we have done is this works, this works, this works, this works. This one is a big value, so n equals 100 compared to the others. Okay, but for this we have picked a very large value of c, which is very close to 7.
So you mean I can choose random numbers, anything I want, but like the most important that it works.
As long as it works, as long as it satisfies the equation.
Yeah, like any numbers.
Yeah.
Okay. Thank you.
Doctor, one small question, please.
Yes.
We can use the negative numbers here about the n. Maybe -1.
Okay, again, we don't want to do that because usually this is reflecting into time, and time cannot be negative.
Okay.
So better not to pick a negative value.
Doctor, in the second example, what was the condition we didn't satisfy, or the equation?
Second example? What second example?
Before the slide. Before the
You're talking
slide.
about the slide?
No. I mean board.
Okay. Here?
Yes. I think you said there is a condition we didn't satisfy, or the equation didn't satisfy.
Okay. See, in essence, this cannot work because when we say n is changing. Okay? It can be anything from 1 to infinity. It will be a very large value. But c is fixed. It's constant. So how can I say that something which is fixed, okay, is bigger than or equal to something which is always changing? It will not work. But that's a good point.
But in some cases will work. Depends on c.
But then they have to be exactly equal. So 3, 3, 10, 10, 1, 1. Okay, they have to be exactly equal. Or in some cases, c would be larger than this. But remember, n is always changing. Okay, so what I try to show you over here is, if I pick a small n, okay, it works with this c. If I pick a bit larger n, it's working with this c. How about if I pick 1, 2, 3, 4, 5, 6 zeros? Would that work? So in this case, I need to have 6. Okay, I guess 7 zeros, 7 nines. I guess. Okay, so it's going to work with this. That should be fine. It's going to work with this. But here, it must always be very close to constant. So in essence, this is wrong. Okay? In other words, what we're trying to tell you is that you should never be able to compare a constant thing with something which is moving. Example, you cannot compare the speed of a car to the speed of a rock. Okay? The car can be stationary. You can put it in a brake. Okay, parking brake turned on, the car is stationary. So as long as the car is stationary, it's comparable to a rock. But the moment you open the brakes and move the car, it doesn't work anymore. So what's the purpose of the car? Isn't it the purpose to make to go from one place to another place? So what you're trying to say is making this comparison itself is wrong. So constant is something which is fixed, and n is the runtime for some program which is running.
So, doctor, we can't even compare the n with the n squared because the n squared is not comparable to the n, right?
Exactly. So these kind of anomalies would happen when you try to pick a function, big O of n, which is not comparable. You're going to get these kind of anomalies, which do not make sense. Here, you were able to do it because both of them were to the order n. If you look at the highest order,
yes,
so this is n, and this is Cn, some constant n. So it's comparable. And we have this constant value. Constants, like I told you, it can be easily ignored.
So can we, with that logic, like, for example, if we have an equation and it's like all constants, can we ignore all the constants and just focus on the n?
Exactly. We're going to see these things later on in the tutorial. Yes.
Okay.
That's what we will do.
Doctor, on the reading in the posted in the website, there is comparison between big O of n and O. There's an O with a line in the middle of n. Is this the same?
I think you're referring to this. There's big O of n, there's big omega of n, and there's theta of n.
Yes.
Okay. Yeah, this is my last slide for today. So this is called big O. Okay. Here we're always looking at the worst case scenario. This is omega. Okay, big omega. This is always looking at the best case scenario. And this is theta. Okay, big theta, big.
I didn't get that. The reason it was theta.
Average case. So, like I said, in this course, we're only focusing on this. Okay. This one we're not covering it. This is going in CS210. CS210. Okay, but just to give you an idea, big O is always close to worst case scenario. Big omega is always best case scenario. And this is average case. And so bottom line is the most accurate one is this one.
Okay.
Okay, but to do this, you need to be really good at math.
Okay.
This involves.
So CS311 is we need math to do it. We need to be good in math.
No, you don't need to know the math. I'm sure you've already studied these things. Okay. Yes. If I want to teach you now, I can't even do it because I know that you guys have finished calculus 1. So you only need calculus. You need integrals, differential equations, and that's it. You can prove it. It's not too hard. If you've done calculus 1, you can do it. But it's just that I don't do these things in my class because sometimes it can be a bit scary for some students.
Okay.
I used to do it before, but people will get lost in the class and they'll start complaining. Come on, this is not a math class. We're studying CS, so I stopped doing it. I only talk about the big O. Okay, some other functions. Let's look at this one. So 3n cubed plus 20n squared plus 5. Okay. I'll do this thing here. So we have 3n cubed plus 20n squared. What was it? Plus 5. Okay, so this is some function, and it says that prove.
It's O of 3.
This is the O of n cubed. Okay, it's a cubic function. So again, what we're going to do is same thing. This is my function, so I'll say 3n cubed plus 20n squared plus 5 should be less than or equal to cn cubed. Okay, that's my big O function g. All right, let's try to solve this. So
get everything on one side and then cn cubed.
Everything over here minus 3n cubed minus 20n squared. Okay.
Shouldn't we take the 20n squared to the other side?
Let's try to do it. So we're gonna have c minus 3n cubed minus 20n squared. Okay. Yeah, let's solve this more. Any ideas?
Do we do the quadratic formula?
Yeah, you move n squared over here. Okay, you can have n minus 20. You get something like this.
Okay.
Okay. Right. But the idea is that we want to separate n from there. So we try to do that. Okay, and I think this is the best we can do. Can't be any more than this. So let's try to work with what we have. Okay, try to substitute some value and see what we get. So we have some value of c and some value of n. Okay, so if I pick c to be 0, or let's say 3, so that's going to become 0.
Yes.
Yes?
Yes, so the n would be 0 as well.
3 minus 3 is 0, 0 times n is 0. So all of this becomes 0. Minus 20.
Yes.
Okay? Minus 20. We said this thing before that we don't want to have a negative value because it doesn't work this way.
We can change the signs.
Okay. So let me show you the solution for this. Okay, it says that this is going to be true for c is 4 and n is 21. So let's verify that. It says when c is 4 and n is 21, it's going to work. Okay, see how? So we're going to have 5 less than or equal to n squared. This is 21 squared. Okay, so 4 minus 3 is 1. And 21 times 1 is 1.
So minus 20. And then...
Okay, so does that work? So 20 minus 20, 21 minus 20 is 1.
Yeah.
We're saying
So...
21 squared.
Yes, it does work.
That works? Yes. So this works. Okay, but what if you pick a different value? Let's pick a different value. Try to go with some other value.
Yeah, we can do 5 and then 22 or something.
Okay, let's say c is 4 and n is 20. Would that work?
No, because 20 minus 20 is 0, and then 0 times n is 0.
20 square, and then, yeah, so that's going to be 20 minus 20. It's going to give you a 0. So all of this becomes 0. So it doesn't work.
Yes.
Okay, so this
So
one
it has
works.
to be more than 21, the n.
So yeah, we can say this thing c is 4 and n is bigger than 21, and this works fine. So the idea is,
this is like the base condition.
We're always playing with the value of n. Okay, remember c can be stationary and has to move. So we should try to find a value of a few values of n, so that we can say that n is moving. So when I say n is bigger than or equal to 21, this means this will be valid for any value of n larger than 21. Equal to 21. Okay, let's look at
Doctor?
Yeah.
Sorry, but we don't divide the 5 by c minus 3 and minus 20.
No, I did not.
Last step.
No, I did not do that. I did not remove it because let's keep all the n's on one side.
Okay.
Bring the n on.
So what's the difference from the past one? And the steps, math steps, last step.
You mean here?
Yeah, here we found the.
Yeah, we tried to do this thing. We tried to do this, and we were able to do it successfully. But here it seems it's not possible. You cannot solve this anymore. Okay, if you try to bring this over there, then you're going to have an n on the left side. We don't want the n on the left side.
Okay. Thank you.
Okay, let's look at
Are we going to be tested to do this?
Are you going to be what?
Tested to do a question like this? On the test?
Well, everything is on the table for now. Okay, so here's the function, and it says prove that this is big O of log of n. Okay, again, we'll thing.
Generally, can see that it is actually that, because like 3 is a constant and 5 is a constant, so log of n is just big O of n, log of n.
Very good for this observation. See, the thing is, what we do is we look for the highest order term. This is the highest order term. All the rest of the terms are smaller than this. So what we do is we just ignore it. Okay, ignore also the constant term, and you're going to get this. Okay, so I will say, okay, I can prove that this is big O of n cubed. Same goes here. Just look at this. Ignore the constant term. Look at the highest order term, which is 7n. Remove 7. Okay, and now you can say, I can prove that this is big O of n. For what value? Simply substitute this value 7 and 2 in there, and you're going to get it. Just very easy. I'm just doing the mathematical way, but you can just look at the function and you can tell. Okay, so same thing, C log of n. Let's try to solve this. C log of n minus 3 log of n. If I rewrite it, I'm going to get C minus 3 log of n. Okay, so how could you satisfy this? Easy. What should be the value?
3.
How about 4?
Shouldn't you take the C minus 3? I mean, yeah, it doesn't matter, but yeah.
No, if you take minus 3, it's going to become minus 6.
No, I mean like C minus 3 to the other side, like divided by C minus 3.
Oh, yeah, sure. We can do this thing.
Yeah, just like
that, C minus 3.
It looks better.
That's fine. We can do that. Yeah, let's do it this way. Okay, so if I rewrite it, I'm getting this. 5 over C minus 3 is less than equal to log of n. Okay, let's find some value.
Okay,
so pick C equals 4.
Mm-hmm.
Okay, so this would be 5 over 1, which is 5. And now we have to find some value for n, so this is bigger. Now, by default, when we say log, okay, we're not talking about log
of 10.
Base 2.
Oh, so yeah, because here's base 2.
Remember something, if n and log of n, okay? So if n is 4, log of n would be 2. N is 8, log of n would be
4.
3.
Oh yeah, 3.
3. This is 16, this would be 4.
4. Mm-hmm.
This should be 32. 6 would be 64, and so on.
Mm-hmm.
Okay, so 1 would be 2.
Yes.
So what should we pick? I want this to be 5 or more.
If we pick 1, it would be 2. It would be so yeah. If we pick 3, then it's more than 5.
64, Victor. We can go for 64.
Yeah, anything bigger than 8. I mean, anything bigger than 3 or bigger.
No, this is 5. Side is 5.
Yeah, so if we put log of 8, then it would be 8. If we put log of 32, then it would be 5.
Yes.
So yeah, log of 32.
So there's your answer. Okay, we can say this again is bigger than 32.
Okay.
Okay, and that should work.
Or equal to.
Yeah. Okay, so these were just some examples. All right. Now let's try to, okay, this is the relationship between big O and growth rate. Okay, big O always looks at the upper bound. Remember I told you that there's always 2 bounds. There's upper bound and the lower bound. Upper bound is close to the worst case scenario. Lower bound is close to the fastest possible time or best case scenario.
Yes.
Okay, big O is always talking about the upper bound or the worst case scenario. Okay, now formally these are the rules for big O notations. So if f of n is a polynomial of degree d, then f of n is big O of n to the power d, for example. Okay, if I have something like 2n, I will say this is big O of n because I'm going to drop the constant over here. If I have 2n squared, I will say that this is big O of n squared. Okay, we ignore the constant term before the term itself.
Mhm.
All right. Same goes with the power. Okay, the power stays. If I have 3n plus 5, okay, this is big O of n because we're going to ignore this constant and we're going to ignore the coefficient of the term. If I have something like this, okay, here, let's do some more practice here. I'm going to write some functions over here and you tell me what is a big O, okay, without proving anything. So 3n squared plus 2n plus 9. What's a big O? Anyone?
N squared.
Look for the highest term. Okay,
Yes.
ignore this and ignore all of this. So this
N
is
squared. Doctor, can we prove it this way? Like, for example, we put big O for each term, and then we keep the biggest big O, basically, or something like that.
No need
Like,
for that because these are very small compared to this one.
yeah, I mean, like, instead of doing the mathematical way of like doing that equation, can we do like big O of n squared plus big O of n plus big O of c, or like 1, and then we remove these because big O of n squared is the biggest one?
I really don't see how that's going to serve our purpose. Essentially, it's just repeating the same thing.
Mm. But like, do we need to do that mathematical way, like the whole thing?
No, if I ask you to prove it, then you have to show me this. If I don't ask you to prove it, I simply say, okay, can I guess what's a big O? So you can just look at it and you can evaluate it like this.
Okay.
All right. Okay, let's pick another function. So let's go with, we have something like 3n power 9 plus 2n power 4 log of n4 plus 31. Okay, what's the big O for this one?
n power 9.
Yeah.
N power 4 log n. Oh,
yeah.
Okay, no, n power 9, yes.
Okay, so we only look at the bigger term.
Yep, okay.
Okay. Now, let's estimate some runtimes. I'm going to give you some program, okay, and we'll try to estimate the runtime for it. So let's say an array is given to you. Okay, so the size of the array is n. And we'd like to add all the values, add everything.
It's a big O of n, basically.
In the array. Okay, that's the problem. And we'd like you to solve the problem. So how would you do it? Should we write our code? Should we write pseudocode? What should we do?
We can do the for loop and then like add elements.
Okay, let's try to go with the for loop. So let's say I have a for loop. Integer I is 0. Imagine this is some method. So we define integer sum equals 0. And let's say this is public. Okay, add. And we passed an array of type integer that already contains the data.
Okay.
So I is less than a.length.
Then
okay.
I plus.
So just to make it more optimal, we can say integer n equals a.length. Okay, we'll talk about this thing later. Why is this important?
Okay.
And let's put n over here. And here I'm simply going to say sum equals sum plus a of I. Okay.
Or sum equal plus.
And I'm simply returning the sum. So that's my program. Okay, so let's try to figure out what's the runtime for this program. How can we do it?
We can take each part and then turn it into a big O notation. So
let's first try to estimate the runtime. Can you give the runtime for this function? We saw this thing last Tuesday.
Okay, without doing the big O thing.
How many operations are there?
So the nth one is constant.
This is going to be one operation. Okay, and here we have integer n equals a.length. for 8 of length, we have to go and fetch the value.
Yeah, so n.
So this
Two
is one
operation.
operation, and integer n itself is 1. So overall, this is 2 operations.
Mm-hmm.
Okay, here this is 1 operation. Integer n, make a new integer and put 0 in there. That's 1 operation.
Yes, and then I less than n.
And we're going to check this how many times?
N times.
N times. And the increment, every time we go and finish the loop, we're going to come back. As long as the condition is true, we're going to increment. So you're going to do this thing n times. Increment it
Yes.
n times. So I can give this thing like 2n plus 1 times.
Yes.
Okay. Now remember, the loop is running only n times. So this equation in itself, we're saying sum equals sum plus go fetch a value from your array. So this one is 1 operation, fetch a value, and then add it and store it. Okay? So usually adding is an operation, and then storing it, updating it is an operation. So if you go this way, that's 3 operations. Okay, 3 operations. But now because this is inside a loop, and the loop is running n times, so we can say all of this runs as 3n times.
Okay.
And now return sum, this is 1 operation. So if you add it up, okay, what equation do you get? This is my runtime, T of n equals to, or in other words, f of n equals to.
So we have 2n.
N.
Yes, 5n plus and then 1, 2.
5? Can I say that?
Oh, yeah. Wait. 1, 2, 4. Yeah, 5.
Okay, so 5n plus 5. So this is my runtime. Now, if you want to prove this is big O of what? How can we do
Big
it?
O of n. Because like the largest value.
So if somebody says prove it.
Prove it, then you do the fn less than.
So you have to do this thing. So 5n plus 5 is less than. Prove it is big O of n. So you're going to do Cn, and let's try to evaluate this just a little bit. So you're going to have Cn minus 5 of n. So equals to n.
C.
Let's bring this thing over here. So C
minus 5, yeah.
Okay. So.
And then you can just
satisfy this with C and
C equals to 6.
C equals 6, very good.
And then n.
Cn is bigger than 5.
1. Oh yeah, okay.
Bigger than 5. Yes. Bigger than 5 should work.
Yes.
Any value larger than 5 would work. Okay. So, so we have proved that this is big O of n. But if I simply ask you, hey, just look at it and tell me if this is big O of n or not, so what are we going to do? Okay, 5n plus 5, just ignore this term, ignore this, and you're going to get n, which is big O of n.
Yes.
Okay, so this is just quick estimation. All right, so this was an example of what we just studied over here. Okay, now, if somebody says, okay, here's another problem. And we have a 2-dimensional array like this.
Oh, so you do 2 for loops.
And we'd like to add everything in this array. This is array A, 0, 1. Let's say this is size n. Let's say this is size n. Okay. We cannot draw n because n could be a large number. So this just
be n squared, basically. Okay.
So if I would like to add everything in there, I have to repeat the same code. I have to repeat
but in
the same code,
2 for loops.
But we have to do it for this many number of rows. So just to give an idea, so here's a loop. Okay, and we're going to loop the run for add all values in row. Row which one? Row, let's say I. Okay, and all of this needs to go under another loop.
And then column.
All values
in column.
Okay, so this is 2 loops.
Mm-hmm.
Now, I'm not going to write code because we will see this thing later, but this is just to give an idea. This is running n times, and the whole thing runs n times. So the overall runtime would be big O of n squared.
N squared, yes.
Okay. Today I also showed you this in the slides earlier. If you have 2 loops like this, the first loop is going from 0 to n, the other one is also going from 0 to n, and they're nested loops, and then the runtime would be n squared. So you can just estimate it like this, just by looking at it. All right, now something which is a bit complicated. Okay, how much time do I have? I have 15 minutes. I have about 15 minutes. Okay, let me start with this. Type, here's a unique problem. Here's an array. Okay, this is just for the sake of explanation. I'm just putting 2 values in there. Sorry, 5 values in there. So I'll put 2, 3, 5, 4, 7. So this is some array. Okay. So this problem is very well known in computer science. It's called prefix averages. Okay.
Okay.
Prefix averages. What it means is I'm going to run this program n times. Okay. Here n is 5. 0, 1, 2, 3, 4. So I'm going to run this thing n times. And every time I'm going to find an average for the 2 values, and then the 3 values, and the 4 values, and the 5 values, and so on. Okay? If you're finding this a little bit difficult, I can give you another example. Let's say, let's go with a simple one. I want to print this on the screen. I'll go print 5 dots on the screen. Then I'll print 4 dots on the screen, then 3 dots, then 2 dots, and then 1 dot. So we're going to get a shape like this. Okay? Or even something like this. 1 dot, then 2 dots, then 3 dots, 4 dots, and 5 dots. So a shape like this. Okay. If you get a shape like this, what is this runtime? What is the runtime? Okay, this needs a bit of careful evaluation. Do you have any questions so far?
Wait, Doctor, the prefix averages, so you add the first 2 and then you add the next one with them?
Yeah, let me do the dots. It will be easier to understand. Once you understand this thing, you'll be we'll move on to the prefix.
Okay.
Anybody else has any questions? Are there people?
Yes, there's a small question.
Yeah.
Can you go back to the previous slide?
Sure.
One back, I think so. Yes, exactly. The plus ones, it's possible, or we may differ that in some of this some places in this function we can add a plus 1.
Where are you talking about? Here, you mean?
Line number 4, exactly.
Oh, you mean here?
In the beginning, the first line, the for loop.
First line of the for loop, yes.
Yes. The I is less than n. We can't say n is n plus 1. I think so. Because since I plus is n times and we are comparing n times, it's going to compare 1 more time, which is the time that it's going to stop. So we can't say that it's n plus 1.
Very good observation. But now the thing is, basically this is running n times. If you're starting at 0, okay,
yes,
it will finish at n minus 1. This is why it's less than n. So this is running exactly n times, not n plus 1 times. If I had put equal to over here, then yeah, you can say this is n plus 1 times.
Okay. I get it.
In any case, plus 1, minus 1 doesn't make a big difference, especially when n is very large. And remember, we're setting big O of n, which is always looking at a very large value of n. We're assuming something worst case, n could be very large, something close to infinity.
Yes.
Okay. So let's try to write a program that's going to work with this. Okay, we'd like to print this shape on the screen. But I'm sure you've done this thing in CS101.
Yeah, I did it.
Okay, so it's just print. So here's a method, public print. Okay, no parameters needed. So you simply run a loop. I is less than n, or we can put integer n over here.
Okay.
Okay, and of course I plus plus. Okay, so here's my first loop, and then I'm going to have another loop. Let's go with j. J is less than n, j plus plus. Okay, and we just simply say print a dot on the screen.
But now it will print a square shaped.
Yeah, and then here, once the one line is printed, we have to say print next line.
Yep.
Next line. Okay, and that should take care of everything. But now the problem is this particular code is not going to print this shape, it's going to print a square. So this means we need to change this. This is not going to work. We have to change this.
Yeah, we can do n divided by 2.
No.
Can we? J is less than n.
First, I like to print five dots, then 4, then 3, then 2, then 1. Can I say j is less than 5 minus I? Can I say that?
5 minus I. Yes, I think. Like if we have 5, then it would be 0. No, I don't think it will work.
So when I start, in the beginning, I would be 0. We come over here. J is 0, so 0 is less than 5 minus 0, which would be 5, which means the loop is going to run 5 times.
Okay.
So it's going to print 5 dots. Okay. Then it goes to the next line. We come back over here, I plus plus. I becomes 1. So we go over here, j is 0. J is less than 5 minus 1, which is 4 now. So this loop is going to run 4 times. It's going to print 4 dots. Okay, get out of the loop, go to the next line, go back over here, I plus plus, I becomes 2. So we go here again, so 5 minus 2 is 3, which means this loop runs 3 times. So you get the idea. It's
gonna print the shape n times, right?
No, it's gonna print only this shape. This is printing dots.
But I less than n, so like if you have 1 million in n, then it's gonna keep moving till 1 million.
Of course, so it's going to have 1 million, then 1 million minus 1, 1 million minus 2, 1 million minus 3, all the way until it becomes 0.
But why is it 5 minus I?
5. Oh, okay. Yeah. So in this case, it should be n, not 5.
Okay. Yes.
Doctor, what if we say integer j equals n, then j minus minus?
Integer j equals 1.
N.
J equals n, and j minus minus. Yes, of course you can play it around. You can do these things. You can start this from n. You can say as long as I is bigger than 0, I minus minus. So yeah, I'm sure you studied this in 101. I don't want to really repeat how to do this thing.
Yeah.
But this is just to give you an idea. Okay. Now, if you like to estimate the runtime, how would you do that? Okay, estimate how many operations are there. So
we do the same thing. So one
operation. This is
n.
1 operation. This is
Wait, isn't it n?
N operations, and this is also
then
n.
n.
So I can say this one is 2n plus 1, like before.
And then J0 is 1.
Now this is one operation.
And this is n.
Okay, we're not exactly sure about this now.
Because I, yes.
5, then become 4, then 3, then 2, then 1, and then 0. Okay, this is what happened. Okay, so it's changing. We're not exactly sure about this. But if we're assuming that this is always a worst case scenario, okay, I can go with 5, which is a value of n. Okay, I know that every time it's going to be less than 5, less than or equal to 5. I can go with n. This is the worst case scenario. Same goes here. This is n. Like we know this thing from experimental evaluation. There will be 5, 4, 3, 2, 1. But we don't really know how to do this thing. So we'll just go with the worst case. That's what we studied. This could be n. So this would be
2n plus 1.
2n plus 1. Okay. And this particular line would be, if this is running n times, worst case scenario, this is running n times. So this would be n squared.
Yes, okay.
Okay. And remember, this loop is inside this loop, which means this loop is running n times. I have to do this and multiplied by the runtime of this line. This line is being n times.
Okay.
And this one is outside. This is only inside the first loop, so this could be n only. Okay?
Yes.
Now, this is a little bit confusing. If you try to add it up, you're going to get something probably more than n squared. Let's try to do this.
Why? It should be n squared. Does it?
So I'm going to get this one. Let's write this down. So I'm getting 2n plus 1.
Okay. Plus 2n squared.
N squared plus
n.
Plus n squared plus n. If you try to solve it, you're getting 3n squared
plus
4n.
4, yeah, 4n, yeah.
4n plus 1. So I'm getting this. This is my runtime.
So yeah, the big annotation would be O(n) squared.
Okay, this is a very large value, 3n squared plus 4n plus 1. So big O, this is O of n squared. Okay.
But this is the worst case scenario.
This is the worst case scenario. Now the thing is, we can estimate, we can optimize this a little bit. In mathematics, okay, if you look at this, what's happening here? What's happening over here is we're printing 5 dots, then we're printing 4 dots. See,
we're doing the exclamation mark thing.
2 dots, 1 dot, and the last one is 0, and then we stop.
Is it?
We stop.
No. Huh?
Okay. So in mathematics, there is something called series. This is equal to, if I have something like this, okay, I can write it like this, n into n plus 1 over 2. Did you guys study this?
Yes.
Yes, no?
But I forgot which kind of series is it. But it's like a type of series.
So if you have something like this, 1 plus 2 plus 3 plus 4 up to n, you can write it like this, n into n plus 1 over 2. Okay? So now the thing is, the same thing is happening over here, especially with this. So we can optimize, we can do a better job at evaluating this function when we're finding big O of n squared. Okay, how so? So
you can use this equation.
Instead, so this one is fine, but this one is not correct. This is what we were suspicious about. We're looking at a very high n for this. So what we can say is this one, okay, let me do the green color. So this one is 1, okay? Because this is inside the first loop, I'll multiply it by n, like what we did before. Okay, and this one is now changing. Okay, both of them are in this loop. Both of them are inside this loop. So I'll say I'll use a series instead. Okay, I'll use a series. I'll say n into n plus 1 over 2. And same goes with this one, n into n plus 1 over 2. Okay, so when I rewrite this, all this again.
How are you going to change it though? Like the J++.
Sorry?
The J++, how are you going to change it to n equals n times n plus 1 over 2?
No, this is, again, we're estimating the runtime because j is dependent on this value. And this is, of course, a function of n.
Okay.
So you can do that.
Okay.
Okay, so this one is going to become n plus, okay, this is this one. And then we're going to add these two. So this is n into n plus 1 over 2, and this is also n into n plus 1 over 2. If you add it up, the 2 will go away. So you're going to get n into n plus 1. So far, so good? Now, this particular line is inside both of these loops. Okay, it's inside both of these tubes. So we can use a series for this. We can say this is n.
Doctor, the use of n times n plus 1 over 2 is not so clear for me.
Okay, again with the series. Remember the series, just a minute ago I told you. So if we have something like this, we can rewrite it like this. So what's happening over here is how many times is this condition going to execute? How many times? Okay, so of course this is n times because of this. It's happening n times. And because this is inside the series, I can estimate it to be the series itself, n into n plus 1 over 2. Same goes with j++. Okay, that's going to depend on the value over here and here because these two are connected together. So I can give it with n into n plus 1 over 2. Now, if you add it up, okay, this is half and this is half. If you add it, it becomes whole. So n into n plus 1, that's what we get. And this n is coming from here, n into 1. So this n comes from here. The print statement is inside both of these loops together. So we can say that both of the loops are given by their runtime is given by the series. So this is one operation, this print. So I'll simply multiply 1 by the series, which is the series itself. And this is inside the first loop only. So it can be given by n. So if you rewrite all of this together, okay, we're going to get the same thing as before. So the blue ones, 2n plus 1, and this n. Okay, remember there's only 4 lines here. So I'm going to get 3n plus 1 plus this n plus, okay,
n times n plus 1.
Let me write it with a different color. So 3n plus 1 plus n plus this n. Oh, sorry, I already did that.
So n times n plus 1.
And then this one. N times n plus 1 plus this one.
Yes.
Okay. So if you add it up, okay, you're going to get an equation which is perhaps better than this. Can we do that?
Yeah, we can. So it's going to be...
Let me take it to the next screen.
Okay.
Try to solve it. Okay, so let's try to solve this. First, add it up. Okay, so we're going to have 3n plus 1 plus n plus, this would be n squared plus n, and this would be n squared over 2 plus n over 2. Okay, so add up all the n squared terms. So it's this one and this one, which is n squared.
So n squared over 2.
3n squared over 2?
Yes.
Okay, now go with the n's. So we have 3n, 4n, 5n. So it's 5.5 n, which can be given as 11 over 2n, 5.5 n, plus a constant term. Okay? So if you do it like this, this is my runtime of function of n. 3n squared over 2 plus 11 over 2n plus 1. Is this better than what we did before?
Yes, it's way less. Less value.
Okay, so yeah,
It's like a simplified version.
Previously we did this one. Let me take this over there. Okay, so I'm comparing this with what we did before. So here is 1.5 n squared. Here we're getting 3n squared. Here we're getting 5.5 n. Here we're getting 4n. And of course, the constant is the same. So naturally, this is going to run faster than this one because the n squared term is almost half. All right. But now remember, when you're estimating in big O notations, okay, we don't have to go
the worst.
We don't have to go too deep. We just look at the worst case, and this is good enough. If you look at it closely for both of them, according to big O, the runtime for this one is going to be big O of n squared, because we're going to ignore the lower order terms. We only look at the highest order big O of n squared. And the same thing would happen over here. So if you're looking at the big O squared, okay, both of them are exactly the same. But if somebody says, no, give me a good estimate, okay?
So use big O theta.
That means you have to come up with this equation, and it's better to do it this way. This is going to give you a better estimation with the series. But if series applies only, okay, remember that series applies only when the second loop's condition is connected to the previous one. How can we know that? This I.
Because n. And, oh, okay.
Here's of I. This I is connected to this I. So if the second loop, the second nested loop is connected to the previous loop, this means they're connected. If they're connected, then you should use a series. If they're not connected, then it's a straightaway n squared.
Okay.
Okay, is it clear or is it too confusing for today?
So if we use the big of theta, it would be more accurate for the best case scenario?
No, don't talk about theta. That's difficult.
Okay.
So try to focus only on big O of n squared. If you understand this, okay, we will go from here tomorrow. If this is not clear to you, we'll be happy to go over this again tomorrow. Okay,
some points are difficult, Doctor.
Okay, don't worry about it. We're going to look at another example for this again tomorrow. Don't worry about it.
Yes, please. Thank you.
But Doctor, the prefix averages.
Yeah.
Can you just like tell us what's going on? Like first we just
I didn't cover it. I'm gonna cover it tomorrow. The prefix averages, I'll cover it tomorrow. Don't worry about it.
Okay.
Okay. Any questions for today? Because I think we're out of time.
Doctor, just one thing. I've seen a memo message or something circling around groups that the final will be conducted at the university, but you are waiting now the approval of the ministry.
Yes, I think we just got a memo now, like when, let me see. I'm checking my email 1 hour ago at 3:30, and it's saying, at least in the memo, it's saying that the final exam would be at PSU.
Yeah. It is, in the end, it will be the ministry's decision.
Of course. I mean, this is the university's decision, but if the ministry decides to make it online, then the university will follow the ministry direction.
Okay.
If there's no clear direction from the ministry, then it will stay like this. The final will be on campus. That's what.
Does that mean that it will only the final? So,
according to this, it's only the final exam. Yeah, but again, I mean, things are not clear, so we'll wait and we'll see. Things will be clear, I think, more after next week, once they decide to open the lockdown. Okay, we'll see how things would be.
Understood.
Okay, so if no further questions, that's it for today. See you, inshallah, tomorrow.
Thank you.
Thank you. You just take attendance once, right?
Yeah. Yes.
Okay. Thank you very much.
Dr.